Are y'all okay with using the number table to simulate an experiment for full credit on the AP exam? Of course, you'll be an advantage when you have the test because you'll have the number table. I know y'all just have it on your Chromebooks now, and I don't expect you to recopy it, but on the test, you're going to have to separate it however you decide to separate your digits, and you're going to have some kind of letter above it to let me know whether it does. We were looking for wearing seatbelts and not wearing seatbelts, so I put W and N above. And I think we talked yesterday about skipping down to the next line. If y'all don't care, let's just continue all the way across because that's how most of the ways the keys are set up for the AP exam. And if we do that, then it'll be a lot easier on me to grade. Otherwise, I'm going to have to look at everybody's individually. I'm trying to think some common errors. This is one mistake people make. You need to put a line when one simulation is over. Make sure that they use the way you write it, that they know that you're taking out the same digits every time. Make sure you have a probability statement. I think that's it. Any questions about how to use the number table? Was anybody confused about why I used 0, 1 through 15? That came from the percent. The reason I did 10 is because they said the police officer stopped 10 people at a time. The percent kind of dictates your number. If 25% was our number, then I would use 0, 1 through 25, 26 to 99, and 0, 0. The reason we have to get 0, 0 in there so it's still 2 digits. The key, y'all have the answer key to this. There's a really good write-up on it. So if you decide you want me to go back and clarify this more, I'll be glad to. Alright, what about number 3? Is 3 okay? This one was one where you assigned them a number from 1 to 8. And I think that one's similar enough to 2 that it should be okay. Number 4, here's how I suggest, at least initially setting these problems up. If you have 2 dice, and you know these dice are not the normal dice because this one has, die A has 4 2s and 2 6s. And 2 6s. And the die B has 3 5s and 3 1s. And we're interested in the sample space of the difference of A minus B. They said, what would happen if you took die A and subtracted die B? And these are all the things that could happen. So you can do 2 minus 5, which is negative 3. 6 minus 5, which is 1. Two minus 1, which is 1. 6 minus 1, which is 5. And that's probably how I would set these up. It's a real simple way to get your, to figure out what's going on. So it says, make a probability model. Well, probability model is just saying what are the things that can happen and what's the probability that they'll happen. So in our probability model, only 3 things can happen. Okay, we can get a negative 3, a 1, or a 5. So our probability model, you get a negative 3, a 5, and a 1. And how do you figure out the probability? Well, you see how many possible things that can happen. So what's the probability of getting a negative 3? Let's see, 1, 2, 11, 12. 12 out of 36, which if you counted all these up, is 1/3. How many ways can you get a 5? 6 out of 36. How many ways can you get a 1? Looks like there's 12, 13, 14, 15, 16, 17, 18 out of 36, which is, so that's the probability model on that. And you could have thought through this without making that, but it's a lot easier if you just write it out, in my opinion. And then that's your probability. Which die is more likely to roll a higher number? So, do you think die A is more likely to roll a higher number, or die B is more likely? It's actually die A. Half the time B rolls a 1. So let's look at that. Yeah. So half the time B rolls a 1. And 2/3 of the time A rolls a 2. So that takes care of that. I mean, there's still sometimes that, you know, the B's going to come up higher. But even if the B rolls a 5, you got a 2 out of 4 chance that the A is going to beat it. So more than half the time, A is going to be higher. Do we want to look at number 5? Yes. Okay. 5 is the one, I had to read through the setup 2 or 3 times to kind of figure out what was going on. And I'm going to go ahead and make it, I'll let y'all be looking at it while I make our table here. Interesting because it was something I didn't know. It says the Census Bureau, each person to choose from a long list of races. That is, according to the Census Bureau, you belong to whatever race you say you belong to. So Hispanic is a separate category, and Hispanics may be of any race. So you may be Asian and Hispanic. You may be white and Hispanic, but that's the only category that works like that. For instance, you couldn't put Black and Asian, but you can put Hispanic and Asian, Hispanic. So I'm not sure why that is, but that's kind of the setup, and that leads itself to some interesting questions about mutually exclusive, which is what they ask us about. Verify that this is a legitimate assignment of probabilities. First thing you want to check, are all these between 0 and 1? Yes. Okay, if we add these up, do they add to 1? Yep. So that's a legitimate assignment of probabilities. So I don't remember any of the questions being like that asked, but that's how you check probability. Adds to 1 and always between 0 and 1. Okay, the first one for B is, what is the probability that a randomly chosen American is Hispanic? Okay, and so for that one, all you have to do is add on this side, and you get 0.14. that one's pretty self-explanatory. Probability that you're Hispanic is okay. According to C, non-Hispanic whites are the historical majority in the U.S. What is the probability that a randomly chosen American is not a member of this group? Okay, so no, we got a not here. Probability that they're not a non-Hispanic white. Well, what I did for this one, I just looked at what was the white non-Hispanic and did it minus 1. So I did 1 minus. We got this. So the probability that you're not a non-Hispanic white is 0.3%. That's the C part. Let's see if I can get D while we can still look at it. Okay. This is actually the one that I thought was good, which is why I was glad y'all asked about this one. Why is white or Hispanic, the probability of white or Hispanic, not equal to the probability of white plus the probability of Hispanic? So what they're basically saying is, why is this not mutually exclusive? Because the only time when you can use or and it be this simple is if they're mutually exclusive. That's if the two things can't happen together. If the Census Bureau changed their mind and said, hey, you can't put Hispanic with white, then we could do this. But as it is now, they're not mutually exclusive because you will have folks that identify. There will be an intersection there of white and Hispanic. So, that's the why, because they're not mutually exclusive. If you did do that, you would end up double counting the intersection. So to actually find the probability of white or Hispanic, you have to do the probability of white plus the probability of Hispanic minus the probability of white and Hispanic. And remember what math operator we associate with and, we're going to have to multiply there. So we've already found the probability of being white. Well, actually we haven't found it, but if you want to find it, it's right here. The probability of being white is 0.813. The probability of Hispanic we did find, minus their intersection, and you do not have to crunch that number unless you just want to. Does anybody, y'all see where the intersection is on our table? If you've got the two-way table, you can do this number, 0.139. You're going to get the same result either way, but it depends on how you want to get there. So if you do all that, oh, that was interesting. My husband's really into Ancestry.com now. I don't know if you've ever seen that, where you pay to have your, he did mine and his and all that. And he spends a lot of time looking at old census reports.
You know, like Mexicans, it's not a race, it's just ethnicity. So like in America, how they explain Hispanics. And like Latins is very different from Hispanics.
And I think all that's interesting, you know, when you start thinking about your background, because, you know, what I thought my background was completely different when I got my results back.
I've seen the video going around, but it's like, I haven't watched all of it, I just watched the beginning of it, and it's like, there's a group of people, they're like interviewing them, talking about like, they're like, oh, I'm Irish, and then like, this Irish guy was literally like, I'm better than you because I'm Irish, and then they found out they weren't Irish, and then heart and stuff, and it's like shocking results, and they're like crying and stuff because they thought they were like that.
And so much of their identity is wrapped up in who they thought they were. Well, like, and I know we are, some of the stuff, they will tell you the way they do the Ancestry.com, they don't pull evenly from both sides of the mother and the father genetically, so you don't get a full picture because they don't pull evenly from both sides, but I thought I had a lot more Indian than I thought I did, and it turns out I'm more mostly English and Irish. So it was just, I just thought it was interesting, but everything's so fluid, I can't imagine somebody thinking they're better than somebody else, that, you know, something silly like that. It's who knows what you think. Okay, so what about, 6, 7, 8, 9, I'll do whatever, or if y'all wanna work, you know, what would help y'all? Do y'all need to see anything else?
On 6, I did the Venn diagram and then checked it, and it was not right.
Okay.
And I don't know what I did.
Okay, so Ramon has applied to Princeton and Stanford. According to his counselor, the probability that Princeton will admit him is 0.4. The probability Stanford will admit him is 0.5. Okay, I tell you what I do on these, honey, and it's just for practice and messing them up so many times. Okay, so I got Princeton and Stanford. I'm sure you've got to there. And let me get some circles going. Overlap a little bit. Okay, so I always start out with where I know the intersection is going to be, and it says the probability that they will both admit him is 0.2. So far so good? Okay. And the probability that Stanford will admit him is 0.4. It might help if I make those different colors. Okay. And the probability that Princeton will admit him is 0.4. Okay, so for right now, this has to equal 0.4. Does that sort of, you have to look at it kind of holistically. The probability that Stanford will admit him is 0.5. And then, well, what does that leave? 4 and 3 is 7. So we're looking at 0.3 right there.
How did you do that?
How did I get to 0.3?
Like 0.2 for Princeton.
Because they said the probability that Princeton would admit him is 0.4. So I know that this circle has to equal 0.4, and I started with the intersection. Okay. Then I said Stanford has to be 0.5, and I already knew 0.2. And then to get this number, I just count. 2 and 2 is 4, 4 and 3 is 7, and that leaves. So what is the probability that neither university admits him? Well, that's going to be this. No, really any math to do this. And the probability that he gets into at least one school, you know, you could do the formula, or you could just count these numbers. Because it's actually, what's the probability he's going to get for Princeton or Stanford? Is, probability of Princeton is 4, probability of Stanford is 0.5, and then you've got to subtract out their intersection. So, but with the Venn diagrams, to make the point about the Venn diagrams, you don't have to do this business. But, you know, I don't know. If they have something where it happens both times, I make a Venn diagram so I can see it up here. That was a good question. Okay, what else? Anything else? 7. Okay. I love tree diagrams. I used to hate them, and now I can't really think through a problem without them. They help me now.
Yeah, they can be confused, but you're right, like when you're doing the problem, they just make it confusing.
Well, you just go up there and all your work is done for you. If you can remember to multiply this way and add this way, you're done. Okay, so they developed a test to detect steroid use. It's always interesting around the Olympics, isn't it, when they start testing those athletes for, and, you know, the athletes are trying to cycle off the steroids in time for it not to show up, and their tests are trying to get better. I always think that's kind of interesting. The swimmers this year are the ones that, the test is accurate 95% of the time when an athlete has taken steroids. It's 97% accurate when they haven't taken steroids. So it's not quite as accurate testing. Suppose the drug test will be used in a population in which 10% have actually taken steroids. Let's choose an athlete at random. Okay. So, to me, the hardest part is reading through all that, but we know we're starting out with an athlete. And they kind of give us some, well, I always do that backwards. 10% have actually used, that's not how to steroids. 90% have not. Now, what else do we need to know? Okay, if you've actually done steroids, then there's a 95% chance they're going to catch you. And there's a 5% chance they're not. And if you haven't done steroids, there's a 3% chance that they're going to say you did. And there's a 97% chance that they're going to say you did. So far, so good. What's the probability that they test positive? Multiply, because here's my two ways they can test positive. Here and here. And then here and here. So 0.095. 0.027. And if you add those together, you get 1.1. Multiply this way. And then the C part, suppose the chosen athlete tests positive. What's the probability that he or she actually used steroids? Okay, so we've got a conditional there. So the probability, the thing that's already happened, they tested positive. What we want to know is, given that they tested positive, what's the probability that they actually used steroids? So the conditional formula says you're going to take the probability of actually used and testing positive over the probability of testing positive. Which we just found, which is nice. We just found the probability of testing positive. And the intersection of testing positive and actually using. So here's my actual users that tested positive is going to be and be careful, because on the test, a lot of folks put, I don't know if they didn't remember that you had to do this time this to get that, the intersection. Is that okay, Jasmine? Do you know where I got the 0.095 from?
Yeah.
Now look, anybody else? You can see that okay there? Yes. The actual used and test positive, I just go start on the branch where they actually used and tested positive. And that'll give you that. I don't know. 7787 is the actual answer. I believe that we got about
It's
5
0.07.
down on up here.
Yeah.
Yeah. That's not that high.
It's really not.
And I'm trying to think through it, given that they tested positive, so we're only looking at the folks that tested positive. We've got them in a room, everybody that tested positive. 78% actually used it. So,
That tested positive.
there's 22 out of 100, if you get 100, there's 22 people that know that didn't do anything. I always struggle when we get to that, I'm good till we get to that point, then I'm like,
I think that would actually be absolutely terrible.
Yeah, false positive, and you can't go to the Olympics.
yeah.
I
So, whatever you